it's not just masses on springs and pendula that exhibit simple harmonic motion. Lots of things do. You can think of atoms in materials as vibrating like they're bound by springs. That's not, of course, how they're bound together, but their oscillations often have vibrational frequencies that are consistent with what we would see with springs, with simple harmonic oscillation. But also, we can go back to the last section we were looking at with buoyant forces and see that if you take an object that's floating and you push it down, so you give it a push down, it can start to oscillate back and forth. Now, this oscillation is separate from ocean waves or something like that, okay? So this is just an oscillation because you displace it from equilibrium. So I want to show you how sort of that works and try to make the case that, in fact, this is simple harmonic oscillation as well. So when we have an object that's just floating, as you can recall, we have that the buoyant force is equal to the weight of the object, right? And to find the buoyant force, if you remember, we look at the volume of water that's displaced underneath. So this buoyant force is equal to the weight of water displaced, or the density of the liquid, right, times the volume that's displaced times g. And so we could call this some distance h, and then it could be some area underneath. So our block could have a cross-sectional area like this, so h. So this volume that's displaced would be A times H. So our buoyant force would be the density of the liquid, A times H times G. Great, so everything's in equilibrium right now. The sum of the forces in this situation are equal to 0. But if we push it down a little bit, so we take our same situation, so I need to have room for the block, so I'll put the block and we'll say that it's lower in the water, okay, some distance lower. So here's the equilibrium line, so that's H. This is some distance Y that you've pushed it down, and then it's going to swing back, then it's going to, it turns out, oscillate back and forth. And it is simple harmonic motion. It turns out that it gets damped very quickly, which we didn't talk about much, but that's the drag that works against it. But we can at least look at it if there's very little drag. And so in this case, notice we still have the same mg, but our buoyant force is going to be bigger, up, right? Because our buoyant force is going to be equal to the liquid, that density of the liquid that's displaced still, times the volume, which would be H plus this Y now, that full height under the water, times A, that's the volume, times G. And this sort of additional buoyant force, so if we look at it, the sum of the forces are going to be then the force buoyant rho of the liquid, H plus Y, A, G, minus mg, and that's no longer equal to 0 as we look at this. So as we look at this, what happens is the rho, well, I'll go ahead and multiply this out, rho of the liquid, H, A, G plus rho liquid, A, G, Y minus mg is equal to 0. This is equal to this. That came from over here. Buoyant force is equal to mg in magnitude. And so what we're left with, I'm sorry, it's not equal to 0. So what we're left with is our extra force, our additional force, if you like, that's acting on it, is rho g rho times a g times y, the distance y. And this is actually a restoring force. It's just like the spring force, if you think about it. So I don't have my signs set up quite so nicely, but when we pull this to the right, and extend it so that the spring is stretched, what happens is it wants to go back to equilibrium, right? That's the direction of the spring force. pulls it back to equilibrium. Well, this is exactly the same way. This y is really a negative value if we wanted to be very careful about it. Or I could just say my force is equal to, then it goes in the opposite direction, minus g of the liquid a g y, where y is now, where our setup is that this is. So if we use our usual sign convention where positive y is up and negative y is down, I really should have changed this to be the buoyant force is h plus absolute value of y, because that y would have been a negative number. So we'll do this. So all told, the force is actually going to be in the opposite direction of y. So if y is negative, the force is up. If y is positive, the force is down. It's a so-called restoring force. So this is the force then that would act to restore it back to equilibrium. Restore back to equilibrium, which looks like the same form as our spring force, like this, where spring force is equal to minus kx. And our oscillation for spring, we have omega is equal to square root of k over m. Well, in this case, the k, what stands in for the k, the restoring force, is given by what I've just circled. So the effective K, the spring force for this restoring force for an object that gets displaced in the water and then oscillates back and forth, that K is just going to be the density of the liquid, the cross-sectional area times G. That would be your K. Your omega is just then equal to the density of the liquid, A, cross-sectional area, G over the mass. And so that can then tell you the period, same thing that happens before, 2 pi over omega. And that can tell you then about how fast something's going to oscillate if you put it in the water and sort of push it down and then it bounces up and down.